Alright, so my name is Frank. I'll be leading this review session. I'm with Shaisto. She's going to be helping lead the review problems. We can get started right now. So, alright. So the exam is going to cover Chapter 8 and Chapter 9. For Chapter 8, we're going to be going over balancing chemical equations, stoichiometry, finding the limiting reactants, and the theoretical, actual, and the percent yield and what they mean. So, as an introduction, balancing chemical equations is important because it shows that we're conserving mass, or it shows that it's following the law of conservation of mass. So we want, on both sides of the equation, we want equal amounts of um, products and reactants in terms of their um, atomic quantities. And you may have to use a trial and approach on some chemical equations. So most of them, it's just required practice. So the rules are to change the coefficient of compounds first before like individual elements. Balance out the H elements first, adding elements first besides H and O. And then once you've done that, then you move on to the H and then the O. If you have polyatomic ions, such as ClO4 right here, treat it as one unit. It's always going to be the same polyatomic ion on both sides of the equation. When use smallest whole number coefficient, which means if everything is a multiple of 2, you would divide everything by 2 to reduce it to the smallest whole number. Don't change the subscripts, which is the small numbers here, and don't add or remove products or reactants. So here's like a tip that I use. When you have like an odd number, when you're balancing an odd number with an even number, and vice versa. For example, like this one. So my phosphorus is a balanced. However, I have 2 chlorine here and 3 chlorine here, and so I can't really um, increase this because it's going to increase by like my even numbers. So what you can do, you can put a fraction in there. So the denominator is the one that how many you have. So in this case, it's 2, and how many you need will be on top. So this will be your fraction, and then just multiply the denominator to turn it back into everything to whole numbers. So this is what you would get. So here are some examples. I can quickly go over them. Okay. So the first example, we have sulfur. We're going to balance sulfur first. We have 1 on each side, so sulfur is good. The next one we would balance its oxygen. So we have 4 on the left and 3 on the right. So here's a situation where we need to balance an odd number with a even number, or even number with an odd number. So what you can do to turn, so we have 4. Let me see if we can write. We have 4 here and 3. Okay, 3 here. All right. So what you can do, you can to change this to 4 to a 3. You can put like a half over here. So this will turn it into 1. So this, instead of 4, this becomes a 3. And so, however, we don't want fractions, so we multiply everything by a denominator, which is 2. So this would be 2, 1, and then 2 here. Oops, 2 here. Alright, it's my PowerPoint is bugging me. Alright, so the next one, we'll balance the any element besides H and O. So we have C, those are carbons, right? So we have 6 here and 1 here. So we could try this, 6. Next, let's move on to hydrogen. 14 here and 12 here. So what we can do, multiply by 7. Now we have 14 both sides. Last thing is oxygen. We have 2 here on the left, and we have 12 on the carbon dioxide, and 7 here. So if I count it out, that should be 19. But that's an odd number, right? So because you want 19, put 19 on top, which is what we have, which is just 2. And now multiply everything by the denominator, right? So you would get 2, 19, 12, 14. So that should be the balanced equation. If you guys have questions, you can raise your hand or turn on your mic or use the group chat. Alright, so stoichiometry. With stoichiometry, you have to remember to balance the chemical equation first. The coefficients in the formula are the mole ratios. So, for example, this is NaOH has 3, H3PO4 has 1. So that means 3 moles of NaOH react with 1 mole of H3PO4. And that goes with the products as well. And you just use dimensional analysis. So when typically the problem will give you a well, they'll tell you what they want, that will be the output here, and they'll give you information, which will be the input. So every stoichiometry problem, you always want to convert to moles, because this is like the language, I guess, that communicates both that communicates each of the reactants with the products and vice versa. So here's an example. What's a minimum mass of Fe2O3 needed to produce exactly 56 of the iron here? All right. Next is first thing is to balance chemical equation, which here we just add 2 on the aluminum and the iron. Next, find out what the question is asking for. Going back to the question, it's asking for grams of iron, and okay, and then what is it giving us? Oh no, it's asking for the grams in Fe2O3, but it gives us grams of iron. Yeah. And then when they give you grams, always try to convert to moles. So we're going from here to here. So here, we need grams of iron to grams of Fe2O3. So convert to moles right here, and then use the mole ratios, and then convert back to grams. So plugging in the numbers, it should look like this. Alright, limiting reactants. So limiting reactants is the reactant that is used up completely, whereas the excess is the one that's left over. Right? There's always a limiting and an excess reactant. So there's different methods to find a limiting reactant. One of them is just use stoichiometry. So balance equation, uh, choose a reactant. So for your example, it would be 2 moles of N2 and 5 moles of H2. So here I chose 2 moles of N2, right? And then you just want to convert it to the other reactant. So converting this one into H2, I do my mole ratios, and then I get 6 moles of H2. So this is how much we need to react 2 moles into. However, we only have 5 H2 when we need 6. So we don't have enough of H2 basically. So that H2 will be our limiting reactant. So that's one way to find a limiting reactant. One way is something that it's something I use. I don't know if anyone if their professor has taught you this, but what I do, I still balance the equation, convert everything to moles. That's already in moles. And then I just compare the equation mole ratio with the given mole ratio. So equation mole ratio would be like, let's say, A divided by B, which is C. And given mole ratio is the one they actually give you. Right? So if the equation ratio is bigger, then the top is the limiting reactant. If the given mole ratio is bigger, then the bottom reactant is limiting. So using that, equation mole ratio is 1, 3, because this is 1 and this is 3, and I get 0.33. Our given mole ratio is 2 and 5. The 2 divided by 5 is 0.4. 0.4 is bigger, so bottom reactant is the limiting reactant. Alright, so theoretical is the same thing as the amount of product you expect. So it's found using stoichiometry when you're using a limiting reactant. Actual yield is the experimental amount that you get, because reactions are never perfect. Your reagent might have evaporated, or you didn't scrape off all the product in your beaker, for example. Percent yield is just actual divided by theoretical times 100%. Okay. All right, so moving on to chapter 19. These are the topics that we'll be going over. So you're gonna come across several terms: solvent, solute, or solution. Solution is the mixture of solvent and solute. It's the mixture of both. Solvent is the medium, usually a liquid, that dissolves the solute, and the solute is going to be the component that is dissolved, which is usually like a solid. So here's a picture to help define the terms. Alright, electrolytes. Electrolytes are substances, or I guess solutions, that can conduct electricity when they're in solution. It is because there's ions that form when they get dissolved, and they're usually going to be ionic compounds and acids and bases. Non-electrolytes are just the opposite. They cannot conduct electricity. So here's an example of an electrolyte. We have ions after it gets dissolved. Here's a picture that compares both. Okay. So strong electrolyte dissolves completely. Um, these can be strong acids, strong bases, and ionic compounds. So these would be these. Um, for for weak, if it's weak, then it doesn't dissolve completely, but it still dissolves, and it still has some ionic um, compounds on it, or ionic charges. All right. One of the things that you have to know and memorize is the strong acids and strong bases. So acids produce H plus in solution, where bases produce OH in solution. So these are common strong acids that will um, really be helpful if you memorize it. So you have nitric acid, sulfuric acid, chloric acid, perchloric acid, um, hydrochloric acid, hydrobromic acid, and hydroiodic acid. And for bases, it just, if you think about it, it's just um, they're like, if you look at the periodic table, they're like on top of each other. So you have one with lithium, sodium, potassium, you have calcium, strontium, barium, all with hydroxide ions. Um, so there's with strong acids, there's also weak acids. They do not dissolve completely. Example would be acetic acid, and then same goes with bases. Weak bases do not dissolve completely as well. And example would be ammonia. There's also two types of acids and bases. With Arrhenius acid or base, acids are the ones that release H plus, and base is the one that releases OH minus. With Bronsted, acids are the ones that donate hydrogen protons, so H plus, or the base accepts hydrogen ions or protons. Right. There's more types of acids and bases, which are basically tells you how many H or OH there is in that compound. So monoprotic, it has one H plus. Mono means one. Polyprotic, poly means many, so more than one, right? So example would be sulfuric acid and phosphoric acid. Here for the base, we have monobasic, which means it only has one OH, and dibasic, where you have two OHs. And whenever acid and bases react, this is typically the format of it, where you have acid and base. If it's strong, you're gonna have the forward reaction would be a lot stronger than the backward reaction. If it's weak, then the forward reaction will be equal to the backward reaction. That is where you get the equilibrium, which is shown with two arrows like this. Okay. Right. So with neutralization reactions, um, that's when you react acid and a base together. So the acid plus base should give you salt and water. The water is formed by the H in acid and the OH in base, and basically a double replacement reaction. Remember that weak acids do not dissociate completely. So if you have strong acid, strong base, like this, it's just a double replacement reaction where it is swap partners, and you get, this would be your ionic equation, and your net ionic would just be the formation of water. Because the rest of these would be like the spectator ions, and so they cancel out. With weak acids and a strong base, you would, because the weak acid doesn't dissociate completely, it will remain in the nationic equation. Same with the weak base as well. It will remain in the nationic equation. Okay. Another thing is something cool is acids and bases can dissolve in soluble compounds. So here MgOH2 is insoluble, but because we added hydrochloric acid here, they did a double replacement. So we have water and MgCl2, which is soluble when in solution. So this is what it'll look like if you do the reaction. With that, with precipitation reactions, this is basically where you have a reaction and a solid is produced, or a precipitate, indicated by an S in the equation like this. Right. With usually precipitation reactions, we have you have to know what molecular ionic and nationic equations are. So molecular is just a regular chemical equation like this. With ionic, we break apart all aqueous solutions, right? Just aqueous. So we break it apart. We add coefficients if we have more than one of them. Like here we have like two NO3s, right? We have to put 2 in front. And then the solids or the liquids, I guess. Anything that's not aqueous or aqueous, whatever, we keep it as is. And then nationic is remove all the spectator ions. So anything that appears on both sides, and then your resulting equation will be your nationic. Right. Another thing it's good to remember is, or good to memorize, is the solubility rules. It helps us predict if a precipitate will form. So there is a way to easier way to remember these. Here's what I used. It's called NAGSAG. NAGSAG. So it's with SAG having the exceptions. So nitrates, acetates, group 1A, which is like the first column periodic table. Then sulfates, ammonium, and group 17, which is the halogens. And the exceptions, you can also have an acronym for it, which is HAPPY Circaba, and then HAPPY for the halogen one, which is HGAGPB, and then Circaba is just SRCABA. So looks like Circaba. Then 17 is just the same thing but no Circaba in it. So another way to remember it is if you know your strong acids, the components of the strong acids will make things soluble. Yeah, besides the exceptions, of course. All right. So redox. Redox are reduction oxidation reactions. So it's where electrons are transferred between reactants. Reduction is when you gain electrons. It's also the oxidizing agent. And oxidation is when you lose electrons, which is the reducing agent as well. Another thing to remember this is oil rig, which is oxidation is loss and reduction is gain. I'm sure there's other acronyms for it, but this is what I use. So with redox, we also have to know oxidation numbers, and it helps us keep track of the atom's charge throughout the reaction. Right. So if it gained a charge, that means it lost electrons. If it became more negative, that means it gained electrons. Right, so rule number 1 with oxidation numbers, elements in their free state are 0. So elements are by themselves or in their free state, so like diatomic compounds would be 0. Number 2, if I sum up all the oxidation numbers in one compound, they should equal overall the charge of it. So NaCl, it's overall neutral. So the individual elements should equal 0. With sulfate, it's -2, so all of these should equal to -2, right? Number 3, if you have an ion, the charge of it is the oxidation number. Excuse me. Right. So you can use the periodic table as a guide. Here's what I mean. I don't know if you guys can see this, but 1A is +1, usually +1. 2A is +2. 3A is +3. And 4A it could either be +4 or -4. It's like in the middle. And then from here, this is usually like -3, -2, -1. Sometimes n can be +5, but that's on certain cases. Right. So we have to also know the priorities. So F, fluorine is always -1, right? And that's the first priority. The second priority is 1A and 2A is +1 and +2 respectively. So here, these are always +1 and +2. Exception is like hydrogen here, but that's if like we have something else that causes it to become -1. And the third priority is hydrogen is +1. So this one would actually just be just the metals. Hydrogen is like the third priority, but here the metals here are always +1 or +2. Oxygen, the fourth priority is oxygen is -2, and then the last priority is other halogens besides fluorine would be -1. Right. So I kind of talked about this already, but if you increase in oxidation number, it's oxidized. Decreased oxidation number is reduced. Right? Reduced is, I think I got this reversed. This should be lost. Yeah, this is gain. Yeah. All right. So here's an example. So let's talk about the chlorine in the equation here. So here, chlorine. See, we're wanting to know the oxidation number from chlorine and ClO minus to ClO minus. Here, with ClO minus, we know that they both add up to -1. So now, however, we know that with our priority groups, oxygen is higher priority than chlorine. So we automatically put -2. And because of that, if we get Cl by itself, it should be +1. And then Cl minus, it's an ion, so its charge is the oxidation number, which is -1. So it went from +1 to -1, and then because of that, it decreased So it means that it was reduced. It reduced is to gain electrons, so it got more negative. So that's why. Another part of the redox reactions is the activity series. So metals that are more easily oxidized will replace the ones that are less easily oxidized. So activity series is what it looks like. Metals at the top will be oxidized easier. Metals in the bottom will be less easier to oxidize. So if it's at the top, this is the equation that you use. If it's lower, you flip the equation. So when you have two metals together, so let's say you have lithium and potassium. Lithium is higher than potassium, so lithium stays as is, and potassium gets reversed. So when it gets reversed, that means it got reduced. And so, nothing about redox is you have to balance redox reactions, and then you can do this by the half reaction method. So step one is find a metal in the metals in the activity series. Right. Step two, find out which one gets oxidized or reduced, depending on how high each one of them are, or which one's on top. And then the one that's on the bottom, you flip it, and then you multiply both equations, both half reactions to match the electrons, and then you combine it. The electrons should cancel out. So example would be chromium and nickel. So step one is to find the chromium and the nickel, right? So if chromium would be right here, nickel would be right here. Okay. So it looks like chromium is higher. It means that chromium is oxidized and nickel is reduced. So chromium, we keep this equation. Nickel, we flip it. Right. So this is what it will look like. Now we want to match electrons. So we have 3 here and 2 here. And to get them to match, we just multiply them with each other. So chromium would be multiplied by 2. Nickel will be multiplied by 3. Like this. We should get 6 electrons each, which cancels out when we add both half reactions. Next thing is molarity. Molarity is the same thing as concentration, right? It's indicated by brackets like this. But the equation is molarity equals moles over liters. You can also rearrange it to find different parts of the equation, but the volume is typically in liters. Here's an example. If I have 45 grams of Ki and then 500 milliliters, so we want to turn this into moles, right? Because that's what the equation uses, the molarity equation uses. So I convert it to moles right here, right? And then I just plug it in to the equation. I should get this as my molarity. Yeah, so it is the same thing, but except instead of finding molarity, we're finding mass, right? Mass, if I go back, is, well, we would use this moles equals molarity times liters, and then we would just convert moles to mass, which we use right here, right? We get mass by itself, so it's really ml, or molarity times liters times molar mass, and then this is what we get after plugging everything in. Okay. Next formula is the dilution formula. It's used when you're preparing solutions. Um, so solution 1 is going to be the original solution, and then solution 2 is your new and prepared solution. M is the molarity and V is the volume. All right. So here's the example. Okay, yeah. So we originally have 1.0 molarity, and our volume was just 5. But we want um, to make a new one that has, we want to put it in the 50 milliliters of water, and you want to know the concentration of it now. Because if I added 5 to 50, it becomes 55 milliliters, right? And I plug everything in, solve for our missing variable, which is M2, and this would be their answer, right? Last thing we go over is pH scale. So here's the equations for it. pH, P, if you think about it, P just means negative log. So with POH, it's negative log of OH, and pH is polarity log of H. And then to reverse it, we just use this 10 to the negative pH for the concentration of this, and then 10 to negative pOH for a concentration of OH minus. Right? It's used to find the acidity, and if it's 7, it's neutral. More than 7 is basic, and less than 7 is acidic. Keep in mind that if you add both of them together, it should equal to 14. pH and OH, pOH. Right. Any other do you have does anyone have any other questions? That's the slide. Okay. This one right? Or this one right? Mm-hmm. Yeah. So after this, we're gonna go over like practice problems. If you would like to stay for that. Do you guys have access to the review problems? These slides are also gonna be posted as well. Right. Okay. Okay. So for this one, it's asking for mass, whereas the other one asking for molarity. Um, you also have to look at what the information they give you. So for the first one, asking for molarity, and they give you kilogram or grams and volume, right? Whenever you approach a problem, always convert grams to moles. I think that's the important thing about calculations and stoichiometry. Is if you see grams, if your first instinct is to convert it to moles. So here we have moles here if we after we convert it, and volume, right? So here we have moles and then volume. So the one that's by itself is what we're looking for. And so here we would use this equation. Second one, um, we have volume and concentration. So we have volume and concentration. Go back. Here we have volume, concentration. So we're solving for moles. Here is asking for mass, but um, mass is just moles times molar mass. And so um, with this equation, I can just convert moles to mass by just multiplying it by the moles. And so um, our final equation would be mass equals molarity times liters times molar mass, which we just plug in numbers. Does that answer your question? All right, cool. All right, let me see if I could share the problem. All right, here's the link. There you'll see the practice problems that we'll be going over. We'll start at 11:50. All right, we can go ahead and start. Shaista.
Awesome. So, hey, Michael, we'll be doing some problems together. So, feel free to, use your mic and work on these with us. So, the first question is saying which chemical equation represents the reaction. So, we have N2 molecules here and H2 hydrogen gas molecules here, and they're combining to form NH3. And we know that because we see one blue molecule and three white molecules in each of our products. So that kind of tells you what's forming. And so for this, you are pretty much just adding up these the molecules. So if you count, there's three N2 molecules, then we have nine H2 molecules, and then if we total our products, we have 6 NH3 molecules. Now, the important thing here is to not stop here because we can actually simplify. So since we see that you can actually divide all of these coefficients by 3, we want to go ahead and simplify that so that our answer comes out to D right here, because 3 divided by 3 is 1, 9 divided by 3 is 3, and 6 divided by 3 is 2. That's kind of how you do that problem. Next question says, what are the stoichiometric coefficients in this equation? So what you should do for this is the first element you should look at balancing is carbon. So if I see I have one carbon on the reactant side and one carbon on the product side, so that means my carbons are fine. Now the next element you should look for is oxygen. So we have two oxygens on the product side, but only one on the reactant side. So you want to go ahead and put a coefficient of 2 on the water. So the only thing left to balance now is the hydrogen. So you can see you have 4 hydrogens on the reactant side and 2 on the product side. So that tells you to put a coefficient of 2 over there. Oh, I'm sorry. We have 4 plus 2. Sorry, 4 plus 4, which means 8 hydrogens on the reactant side. So that tells you you need a coefficient of 4 on the product side. Does that make sense, Michael? Cool. Next question. Okay, awesome. What mass of lithium nitride is produced when 75 grams of lithium metal reacts with the nitrogen according to the equation. So for these stoichiometry math problems, you should start with what is given. Now, the only mathematical information they gave us so far is that we have 75 grams of lithium metal. So, and what are we solving for? We're solving for mass, so grams of lithium nitride. So, you should first check to see, is your equation balanced? In our case, it's already balanced, and it's really important because we use the coefficients from the balanced equation for our stoichiometry. So like Frank was saying, you should first convert from grams to moles. So 6.9 grams is how much 1 mole of lithium weighs. So that cancels out our grams. Then we have 6 moles of lithium. And for every 6 moles of lithium used, 2 moles of lithium nitride are produced. That's where the stoichiometric ratio comes into play. And now we convert back to grams using our molar mass. So 1 mole of lithium nitride, I believe is what it's called, weighs 34 grams. So look, to cancel out, what goes on top must go on bottom. And when you solve out the stoichiometry, you get 125 grams as your answer. Moving on. Next question, what mass of iron oxide must react with carbon monoxide? So, oops, I need a pen. We're looking for grams of iron oxide must react with carbon monoxide to produce 124.5 kilograms of iron metal. So now they gave you how much product you have, and you kind of need to work backwards to see how much reactant do you need to make that much product. So again, we start with what is given, which is how much product we have, 124.5 kilograms. Okay, I'm just gonna take up space here and then I'll erase it before we go to the next question. Okay, 1 kilogram is 1,000 grams. You gotta get into grams first before we can go to moles. And then 55.8 grams are in 1 mole of iron. And now we use our mole to mole ratio, 2 moles of iron, take 1 mole of iron oxide. I apologize for my handwriting. And 1 mole of iron oxide weighs 160 grams. And when you do the stoichiometry, you are going to end up getting, you're going to get 178 times 1,000 grams, and you would convert that back down to 178 kilograms. Are you guys okay with me erasing this, Michael? We will post the key later. Okay. Yes, Michael. You have a question? Did you have a question, Michael?
He might be typing.
He might be what?
He might be typing.
Oh, typing. the mole ratio is flipped for the reactants. So are you saying that from the other question we went from like reactants to products, and in this question we're going from products to reactants? Okay, yeah, exactly. So there's only really one format to ask these questions. They have to give you something and then you have to solve for the other thing, probably on the opposite side of the equation. So yeah, I'm gonna erase this really quick. Michael, do you have access to a microphone on your laptop by any chance? So there's not like a huge delay. Okay, I'm going to start on the next question. Now it's asking how many moles. Okay, so if you can and are comfortable, I would love for you to use the microphone so we can like talk to each other, and I think the learning would be a lot better. How many moles of NH3 can be produced by the combination of 3 moles of N2 and 1.5 moles of H2? So this is back to the first equation we were working with. Hydrogen gas plus nitrogen gas makes ammonia. First thing we should do is balance our equation. I feel like balancing is the thing people forget the most. Okay, now it says we have 3 moles of nitrogen gas, moles, and 1.5 moles of hydrogen gas. So we're
The
looking for,
3 should be in a H2.
oh, thank you, 3 moles of N2. Wait, did I not write that? 3 moles of nitrogen and 1.5 moles of hydrogen?
Oh, no, like the balance equation, I mean.
Oh, my bad. 3H2, 1 mole of N2. Thank you. So the different thing here is that they didn't give us the information about just one reactant, they gave us the information about both. That means that we have one limiting reactant and one excess reactant. Now we have to figure out which one is our limiting reactant, because since that reactant isn't limiting, it's going to determine how much product is going to be formed. If you use the excess reactant, then you're going to get more product than you'll have in reality. So there are a couple different ways to figure out what is limiting and what is excess. We'll do one way on this problem, and then on another one we can do a different way so you can see all of the different methods. So what I like to use is that so it says I already have moles of each, so I like to divide them by their coefficients. So 1.5 divided by 3 is 0.5. And 3 divided by 1 is just 3. So I just divided them into like a proportion to see how much of each I have, and I have a lot less H2 than I have N2. So that tells me that hydrogen gas is my limiting reactant, and that's what's going to determine how much products are made. So I'm going to start with 3 moles of H2. I'm sorry, 1.5 moles of H2 is what was given. And for every 3 moles of H2, 2 moles of ammonia are produced. So when you do the stoichiometry for it, 1.5 times 2 is 3, 3 divided by 3 is 1. So 1 mole of ammonia would be produced. Any questions, Yaride or Michael?
I have a question.
Yeah. Was it Yara that was speaking? We can't hear you.
Seems like it keeps getting disconnected.
Yeah, maybe you can try typing it, Yara. It was Michael? Okay. Yeah, what's up, Michael?
So on this problem, you would only be dividing the reactant instead of the product, right, by the coefficients?
Correct, because they gave us how many moles of reactants we have. That's why we're able to do that. They didn't, we're solving for moles of products, so that's why, yeah. Does that help? And like the thing I kind of use as my like checker is that is everything canceling out. So I have moles of H2, moles of H2, and that's what leaves me with moles of ammonia. Okay. Okay, so next question saying what mass of calcium sulfate is produced according to the given equation when we have 5 grams of each reactant. So again, they gave us the information for 2 reactants, so it's up to us to first figure out which one's limiting before we start our stoichiometry. So we have 5 grams of each, and we're solving for grams of calcium sulfate. I like to just indicate what am I solving for. So you should convert from grams to moles, and when you do that, you get 0.06 moles of calcium fluoride, and you get 0.05, that's a 5, moles of sulfuric acid. So now, so these, the coefficients here are 1-to-1. They're present in a 1-to-1 ratio. So you can just see which one is less. So since I have less sulfuric acid than I do calcium fluoride, that tells me that sulfuric acid is my limiting reactant. So that means I can start my stoichiometry from there. So 5 grams of H2SO4. And of course, I need to convert from grams to moles. 98 grams in 1 mole. Then for 1 mole of sulfuric acid, 1 mole of calcium sulfate is produced, and 1 mole of calcium sulfate weighs 136 grams. So when you do the math here, it comes out to 6.94 grams of calcium sulfate are produced. Cool. Next one. What mass of water is produced by the reaction of 50 grams of, how did you determine the limiting reactant? So they told us that we had 5 grams of each reactant. So we converted each reactant to moles. And then if we see, I have 0.05 moles of sulfuric acid, which is less than 0.06. So that tells me since I have less sulfuric acid, that's my limiting reactant. Awesome. So next question, what mass of water is produced by the reaction of 50 grams of methanol with an excess of oxygen when the percent yield is 53.2%. So we're not going to worry about the 53.2% yet because it's saying what mass of water is produced. So we're looking for grams of water, and they're saying 50 grams of ethanol. And then they were nice and they told you that you have an excess of oxygen. Since they came out and told you oxygen is your excess reactant, you don't have to worry about limiting. And you just start from what is given, which is 50 grams of methanol, 3OH, convert that to moles. Let's see, we have 32 grams and 1 mole of methanol, and then we use our stoichiometric ratios. So 2 moles of methanol produce 4 moles of water, and 1 mole of water is 18 grams. So when you go ahead and multiply all of that out, you get that 56.2 grams of water is produced. Any questions on this problem? How come you didn't do anything with the percent? So the reason why we didn't need to do anything with the percent is because, so percent yield, the formula is actual over theoretical, okay, pretend that's theoretical, times 100. And they didn't really ask us for anything here. They told us the yield is 53.2%. So a follow-up question could be that if the yield is 53.2% and what we solved for right now is the theoretical yield, so they could ask us what's the actual yield. But they didn't ask us any type of follow-up question. They just asked us to solve by stoichiometry the theoretical yield. So there's not a reason to take into account percent yield. We're going to do another question in this packet where it actually asks us to like calculate the percent yield, and that's where it's more relevant. Do you have anything to add on this, Frank? That's kind of it, right?
Yeah, that should be it.
So if they would have said that what is the actual yield of water when the percent yield is 53.2%, then we would have had to use that formula. Awesome. Okay, consider the reaction. I'm tired of blue. We'll use green. You have 0.86 moles of MnO2, 48.2 grams of HCl. Which reactant will be used up first? So they're asking you what's the limiting reactant and how many grams of chlorine gas will be produced. So they already gave us moles of MnO2, so we can start by converting the hydrochloric acid to moles as well. So when you convert the 48.2 grams to moles, you get 1.322 moles of HCl. So you're comparing 0.86 moles with 1.332 moles, and then what I like to do is I divide by the coefficients. So the coefficient of MnO2 is 1, so that means that, we're sticking with 0.86. And then the coefficient of HCl is 4, so I would divide this by 4, 1.322. And I get 0.3305. That means I have now when comparing these two proportion numbers, it shows that I have a lot less HCl than I do MnO2. So that means HCl is my limiting reactant. So I'm going to use that to determine how many grams of chlorine are produced. So I can start with my moles, 1.332 moles of HCl, 4 moles of HCl are used for every 1 mole of Cl2 produced, and 1 mole of chlorine gas is 70 grams. So when we go ahead and do the math there, oops, okay, we get 23.4 grams of chlorine gas is produced. Okay, next problem. Lithium reacts with nitrogen to form lithium nitride. What is the theoretical yield? Okay, so this problem, we'll get to use the formula. How come you didn't use the 0.3305? So that's kind of a bookkeeping number. We just divided that to see for every 1 mole of MnO2, like how much HCl do we have? So like it says we have 0.86 moles of MnO2 and that has a coefficient of 1. And we have 1.332 moles of HCl, but that has a coefficient of 4. So to kind of balance everything out and to compare like in a 1-to-1 setting, we divide it by 4 and we get 0.3305. But that number is just something that allows us to compare to figure out what the limiting reactant is. My moles are this number. But if you see, we do end up kind of using that number anyways, because what did I do here? I divided by 4 to get this number. And then I did that in my stoichiometry as well, because every 4 moles of HCl used, 1 mole of chlorine is produced. So we kind of did use it there as well. Cool. So now we get to do an actual theoretical yield problem. So it says 12.3 grams of lithium are heated with 33.6 of grams of nitrogen gas. If the actual yield is this, what is the percent yield? Awesome. So the formula for actual or percent yield is actual over theoretical times 100. And that gives you percent yield. So from this formula, they are asking you the percent yield. They gave you the actual yield, and this is times 100, so you don't have to worry about that. So before we can figure out the percent yield, we need to figure out the theoretical yield, the denominator. So theoretical yield is what is expected to be produced, by the mathematical numbers only. Like in the best case scenario, when everything goes perfectly in your reaction, in your lab, this is how much product should be produced. Actual yield, on the other hand, is what happens in reality, because we know in a lab setting, things go wrong, yield gets lost, contaminants are found, so you often end up with less or more than what you are expected to produce. So that's kind of what percent yield is talking about. So before we can get theoretical yield, of course, we need to find our limiting reactant. So you should convert lithium and nitrogen to from the grams they gave us to the moles. So we end up with 1.7 moles of lithium, and we end up with 1.2 moles of nitrogen. So again, here we can do a different way for our limiting this time. So another way to find out which is your limiting reactant is to just start with one and see if you have enough of the other to react with it. So if I have 1.7 moles of lithium, and for every 6 moles of lithium, 1 mole of nitrogen gas react with it, and 1 mole of nitrogen gas weighs 28 grams. So when I multiply that out, I get 7.9 grams of nitrogen are required to react this much lithium. Well, I have a lot more nitrogen than 7.9 grams. So since I have a lot more nitrogen than what I need, that tells me that I have nitrogen in excess and that lithium is my limiting reactant. So now I can go ahead and use lithium to find my theoretical yield. So 1.7 moles of lithium, 6 moles of lithium yields 2 moles of lithium nitride, and 1 mole of lithium nitride weighs 35 grams. Now, when we multiply all that out, we get a theoretical yield of 20.6 grams. And now we need to plug it into our formula. I'm going to change my color so you can see better. So they told me actual is 5.89. Theoretical we just solved for is 20.6. And these are both in grams. And then we multiply by 100. And we get the value of 28.6%. So we only got about 28.6% of product than what we expected. So that's kind of how you do a limiting percent yield problem. Does any questions here, Michael? I know it's a lot of steps. Awesome. I'm gonna erase the board, and then we have one more problem like this, and then we're gonna go into some more conceptual stuff. So what is the maximum mass of P2I4 that can be prepared from 7.25 grams of P4O6 and 12 grams of iodine? So we're looking for the grams of product, and they gave us the mass of our two reactants. So once again, we need to figure out which one is in limiting, which one is in excess. So the third way to find out what your limiting reactant is to use both of them to figure out how much product is made, and then whichever one produces less product, that's the one that's the limiting reactant. So we can go ahead and do that method next. So they told us 7.25 grams of P4O6, and that converts to 0.03 moles. And they told us 12 grams of iodine, and that converts to 0.04 moles. So we'll go ahead and start for P4O6 first. So 0.03 moles of P4O6. 5 moles of P4O6 produce 4 moles of P24, our product, P2I4. And 1 mole of our product weighs 570 grams. Wow, that's heavy. And when you solve for that, you get 15 grams of product are produced. And that's with P4O6. Now we'll do it for our other reactant, which is iodine. So we have 0.04 moles of iodine. And then if we look at the coefficient, 8 moles of iodine produce 4 moles of product. I'm just going to write product. Okay. 1 mole of our product weighs 570 grams. 7. And then when you multiply that out, you get 13.5 grams of product. So if we compare, and this is with our I2. So if we compare how much product is produced by I2 versus product produced by P4O6, you see that I2 produces less of our product. So that tells us that I2 is the limiting reactant and this value is the correct mass of product form. So that's the third way to find your limiting reactant. How do you feel, Michael, about all this math and limiting stuff and all the different methods? Is there one you like better? So the next stuff we're going to do is we're talking about, I like just converting the reactants to moles because it's easier for me to see which one is limiting. I agree. That's the one I prefer as well. But when you do convert reactants to moles, you do have to look at those coefficients, right? To make sure that you are looking to them at a one-to-one setting rather than what's given. So do you do the method where you divide by the coefficient number, Michael? Okay, awesome. Yeah. Cool. So now we're going to move on to some electrolyte stuff. So soluble ionic compounds are, so keyword, if it's soluble, then it's a strong electrolyte. So strong electrolytes are things that dissolve in solution, any kind of salt, things like that. Now it says soluble molecular compounds. So if it's a molecular compound, it's not like where we have a cation and anion and they're dissolving in solution, right? That's ionic. So molecular, we can't say if they're always strong or not. So we can say sometimes they're non-electrolytes because example of a molecular compound that is a strong electrolyte would be our strong acids. But other than that, most molecular compounds are probably not soluble. So that's why you can say sometimes. Which of the following compound is a strong electrolyte? So for this, you should look for a salt. HF might be tempting because it looks like some of our strong acids, but since it's not on our 7 strong acids list, it's not a strong electrolyte. It's a weak electrolyte because remember, our strong electrolytes and our strong acids dissociate 100% in solution, but things like HF, HCN, H2O, those are all weak acids, so they don't dissolve 100%. NaF is the only salt. We have our cation and anion, so those would dissolve in solution. And NH3 is a weak base, so that's not a strong electrolyte as well. Yes, Michael. Did you choose NaF because Na is a group 1A element? Yeah, so the group 1A elements are always going to be soluble no matter what they're paired with. Yeah. And like NaF is an ionic compound. It's made up of a cation and anion. So in solution, those come apart. So like if you remember when we were like balancing equations, and I think we're going to talk about net ionic equations later, these compounds would be spectators because they dissolve completely and they don't really participate. Does that help? Cool. Which of the following are water soluble? So for this, there's a set of solubility rules you have to memorize. There's a chart, and that tells you all the compounds that are not soluble. And anything that's not on that list is soluble. So anything with the bromine is completely soluble. Anything with sodium is completely soluble. Anything with acetate is completely soluble. Carbonates are not soluble, and anything with mercury is also not soluble. So for that, it's kind of just a little bit of memorization of knowing which are soluble and which are not. And then this second one as the opposite, so which are water insoluble. So that's going to be our chromates, our phosphates, our sulfates. Those are all insoluble. So right here, you might be tempted to say, well, this is paired with carbonate, so it's insoluble. But since it's a group 1A element, lithium, that's always going to be soluble no matter what it's paired with. So that's why we don't select that. Okay, net ionic equation for the combination of iron nitrate and sodium carbonate. So this is what's called a double displacement reaction. Let's write out what happens first. Iron nitrate combines with sodium carbonate. And basically these pairs flip. So then we get iron carbonate. And notice how I know the charge of the iron. So we know nitrate is -1s. And since there's two nitrates paired with one iron, that tells us the charge of this iron is +2. And then you know that carbonate has a -2 charge. So that's why I'm able to form this compound and I don't need any subscripts because I have a +2 iron and a -2 carbonate. And then our last thing is going to be sodium nitrate. So you should immediately see that, we have sodium nitrate, 100% soluble salt. So it's actually going to be a spectator. So I'm going to write out what's called the total ionic equation. So basically anything that's a salt and like 100% soluble, you write it separately. Where's my pen? Because in reality, if you have a salt like these, that means in solution, they don't exist as iron nitrate. They exist as their individual ions because that's what they dissociate into. I'm gonna put 2 there. Now, on this side, you need to be careful because this product that formed iron carbonate, that's actually a precipitate. It's a solid. And you know that from your solubility rules where you see that things paired with carbonate are not soluble. So that's going to stay together because if it's a solid, it's not dissociating. So on our product side, we have iron carbonate, sodium, and nitrate. Cool. Now, this is your total ionic equation. The next step is to cancel out things that appear on both sides because if an ion appears on both sides of the equation, that means it's not participating in the reaction and it's a spectator. So if I see sodium comes up in both sides and nitrate comes up in both sides. And what I'm left with is iron plus carbonate forms our solid iron carbonate, and that's your net ionic equation, and that corresponds to answer choice B. Yes. How come you canceled out the NO3? Well, actually, if you went ahead and balanced this, then you would get 2 NO3 on this side and 2 Na, and that's the same. So in the beginning, I probably should have balanced our reaction equation. Since I have 2 sodiums on this side and 2 nitrates on this side, I needed to put a 2 here. And that's how we get 2 of these ions and cancels out with the other 2 ions. My apologies. Does that make sense? Cool. Next question saying, write the ionic and net ionic equation for the following reactions. It's going to take a lot of space. So, draw. Again, these are double displacement reactions, so you can just kind of flip the pairings. So we're going to have NaCl, and there's going to be a coefficient of 2 right there, plus zinc sulfate, and zinc sulfate is a solid, so your net ionic equation is basically going to take out this sodium, take out the chlorine, so that we're left with sulfur plus zinc gives me zinc sulfur. Zinc sulfide would be the correct term. Does this make sense right here, Michael? Or do you want me to write out the total ionic equation as well? Awesome. So the next pairing that is going to produce KNO3 and strontium phosphate. It's going to be 3PO4. And we can go ahead and add can balance the reaction. So I have 6 and 6. 3 strontium, 1 phosphate, 1 phosphate. So this is what our balanced equation would look like. And then if we convert it to our net ionic equation, we would see that the nitrates cancel out, the potassiums cancel out, and we're left with phosphate, 2PO4, 3 minus, plus strontium, so it should be 2 plus. Yeah, gives us strontium phosphate, which is our solid precipitate. I'll do the last one down here. We have magnesium nitrate and sodium hydroxide. The products that are going to be formed are magnesium hydroxide, which is a precipitate, and sodium nitrate. We can go ahead and balance. So we have the 6 here. I'm sorry, a 2 there. And what that would look like when we canceled out the nitrate, we cancel out the sodium, we end up with magnesium plus hydroxide yields magnesium. So 2 plus hydroxide. So for these, you kind of just need to make sure that the charges match. So since magnesium has a +2 charge, you need 2 of those -1 hydroxides to form the compound. Alrighty. Identify the Bronsted acid. So key thing about a Bronsted acid, it donates hydrogen ions. So you want to see which compound is donating its hydrogen. So if we look at NH3 on the reactant side, we have 3 hydrogens, and on the product side, it has 4 hydrogens. So NH3 is actually gaining a hydrogen, which means it's actually a base. So our other option is H2SO4, where we see it is donating its hydrogen to NH3 in order to form this compound. So our answer is A. Are you okay with that, Michael? I'm going to go ahead and skip this one right here because it's more net ionic stuff. I feel like we've done enough of it, and I want to get to the rest of the questions. We'll go ahead and skip that bottom question. How did you know that H2SO4 donates the hydrogen? Well, if you see on the product side, H2SO4 donates its hydrogen to NH3, and that's what makes NH3 into this ammonium ion. And that's how, because what we have right here is an ionic compound. So you know that H2SO4 donated its hydrogen because you see that NH4 and it looks like this cation right here. And since this ion was formed, that's how it was able to combine with the sulfate to form that compound. So it needs to receive hydrogens from somewhere, and H2SO4 would be the place that donated. Okay. Okay, now we're getting into redox. So it's asking about the reducing agent. So asking for the reducing agent is another way to ask what is oxidized, which species is oxidized. And remember, oxidized means you're losing electrons, so you should see the oxidation number getting more positive. So the first thing you should do here is assign oxidation numbers everywhere. So magnesium has an oxidation number of 0, chlorine -1, hydrogen +1. Magnesium on this side is +2, chlorine is -1, and hydrogen gas is 0. Hydrogen is 0. So reducing agent, we're looking for our oxidation number to getting more positive. So we can see that in magnesium because it has an oxidation number of 0 and then it becomes +2. So it means it lost those 2 electrons, and that's why our answer is A. Next question. According to the activity series, which of the following redox reactions will occur? So to do these problems, you need to see on the reduction potentials chart, something that's getting reduced needs to have a higher reduction potential than the thing getting oxidized. That's the only way that reaction will proceed. If something is getting reduced, you see by their oxidation numbers, but it's lower on the reduction potentials chart than the other species, that reaction is not possible to occur. So if we look at our first equation, we have iron, and it's going from an oxidation state of 0 to +2. So that's getting oxidized, and nickel is going from an oxidation state of +2 to 0. So nickel is getting reduced, and iron's getting oxidized. Now I need to check my reduction potentials chart to see, is nickel above iron on the reductions potentials sheet? So since it is above iron, that means nickel is able to get reduced in the presence of iron. So this redox reaction would occur. I don't think we have a chart with us, but you could look up a chart online to just like confirm the numbers and see how nickel lies higher than iron on the chart. Oh, awesome. So if we look at our next question, not question, our next part. So tin is going, it's being oxidized. It's going from 0 to +2. Lead is going from +2 to 0. So kind of exactly what was happening in part A. But only thing now is we need to check, is lead above the reduction, is lead above tin on our reduction potential chart? Does lead have a higher reduction potential than tin? If so, the reaction will occur. So it is true, it does. So this reaction is able to proceed. Now let's look at our part C. Magnesium is getting oxidized here, again from 0 to +2. And we have barium is going from +2 to 0. So same numbers we're working with. Barium is getting reduced in this problem, and magnesium is getting oxidized. However, when we look at the reduction potentials chart, barium is not above magnesium. Magnesium is actually higher. It has a higher reduction potential. So that means that that redox equation cannot occur. So if we apply the same logic on part D, we have lead is being oxidized from 0 to +2. Platinum, I believe, PT, is being reduced from +2 to 0. We need to locate them on our chart. Platinum, it has a higher reduction potential than lead, so that reaction can occur. And then lastly, we have zinc is becoming oxidized, 0 oxidation state to +2. Calcium is being reduced from +2 to 0. So now we need to make sure that calcium is above zinc on our reductions potentials chart. And unfortunately, it is not. So that does not occur. And I hope I said that this one does occur. Maybe I forgot to circle it. Does the redox stuff make sense? I think that's our last question on redox. If you have any questions here, I can answer that. Yes. if the metal that is not oxidized is higher than the reaction than the other metal, then the reaction can't happen. If the metal that is not oxidized, so if the metal that is reduced is higher than the other metal, no, then that means the reaction does happen. So the metal that's getting reduced needs to be higher on the reduction potential sheet than the metal that's getting oxidized. And that allows the reaction to proceed. So for example, if nickel had a reduction potential of 2 volts and iron has a reduction potential of 1 volt, since nickel's getting reduced in the problem, nickel needs to have a higher reduction potential for this reaction to proceed, and since it does, then I can circle it. In our part C and part E, those values did not correspond. Barium is lower on the sheet than magnesium, and calcium is lower on the sheet than zinc. So that's why those reactions can't happen. Okay. So now we're going to do some stoichiometry stuff. Calculate the molar concentration of a solution by dissolving grams of NaOH into water to yield 1.25 liter. Oh, my bad. Okay, molar concentration. So what is happening? Okay. Molarity is what you're solving for, and I like to write out what units I'm looking for. So molarity, you need moles over total volume, liters. So they gave you what to plug in for liters, 1.25. You need to figure out moles. Well, they gave you grams. So you need to convert from grams to moles. So when you convert 58.5 grams of NaOH to its moles, you get 1.46 moles of NaOH. Then you need to divide this by the total volume, which is 1.25 liters, and then you get your molarity of 1.17 molar. So just look at what units you're looking for, what do they give you, and see how can I convert. And molar mass is a common thing you're going to use. Okay, next problem says determine the pH of a solution. So the formula to find pH is a negative log of the concentration of hydrogen ions. So they gave you your hydrogen ion concentration here, so you can go ahead and plug it in and take the negative log, and you get an answer of 7.2 pH. What mass of glucose in grams must be used to prepare 500 milliliters of solution with this molarity? So you're working a little bit backwards. So let's understand what this 2.050 means. It means you have 2.5 moles of glucose in 1 liter of solution. Now, they told you you have 500 milliliters of solution, and they want to know how many grams of glucose is in there. So you use the volume that you have to convert to how many moles you'd have in that volume. So 500 milliliters is the same thing as 0.5 liters. So that allows me to cancel out my liters and tells me that in that solution that they're talking about, I have 1.25 moles of glucose. Now you can't stop there because they asked for mass. So you need to convert the 1.25 moles of glucose to mass by multiplying by its molar mass, and you get 225 grams of glucose. Okay, next problem. For a solution that's 0.18 molarity sodium carbonate, yeah. On the bottom of 0.5 liter, is there anything that's supposed to be there? No, because you're just solving for moles, so you're just trying to cancel out the liters, so you don't need to put anything on the bottom to do that. If it helps you to kind of like understand though, you could label this 0.5 liters in the solution that's in the problem. So then if you look at what you're left with, you have that you have 1.25 moles in your solution. So if that helps you, you could definitely add that there. But math-wise, you don't need anything. Cool. Next problem is saying for a solution that is 0.18 molar, express the concentration of the individual ions. So for this, you need to look at the stoichiometric ratio. So since sodium is a +1 cation and carbonate is a 2 minus a polyatomic ion, you need two of the sodiums to neutralize that one carbonate ion, right? So that means you're going to need twice the amount of sodium than you have carbonate in order to get this neutral compound. So that's what tells you that you need to have 0.36 molar in sodium for 0.18 molar carbonate. A way you can see that stoichiometrically is 0.18 moles or molar sodium carbonate. I'm going to do this. 0.81 moles of sodium carbonate in 1 liter of solution. That's what that 0.18 molarity means. And 2 moles, 1 mole of sodium carbonate has 2 moles of sodium ions. So if you do this stoichiometry, you can see that you need to multiply the 0.18 by 2 to get the molarity of the sodium ions, because you'd be left with moles of sodium ions over a liter of solution. So, and then to do the same thing for carbonate, you can start off with 0.18 moles of carbonate, sodium carbonate, in 1 liter of solution, and 1 mole of sodium carbonate requires 1 mole of carbonate. How do you know that? Well, that comes from that compound, and that tells you that it's just 0.18 times 1, so 0.18 molar carbonate in solution. Does that make sense? It does make sense, and writing it out really helped me understand it. I'm glad. Sorry, it's really messy. but I'm glad that helped. Okay, so our last question says, what volume of 0.144 molar of sulfuric acid is required to neutralize 25 milliliters of 0.041 molar hydroxide? So for this, let's first write out our equation for what's occurring. So we're combining sulfuric acid with barium hydroxide. We're going to end up with water. And barium sulfate. Cool. They're asking for how many milliliters of acid we need to neutralize this amount of barium hydroxide. So they gave us milliliters of barium hydroxide, but they also gave us the molarity. So when we have the volume and the molarity, we can use that to convert to moles of barium hydroxide. And once we get moles of hydroxide, we can use that to see how much acid we're going to need to neutralize, because we want this, in order to neutralize the reaction, we need an equal number of hydroxide ions and hydrogen ions in order to get this water. So let's start off by converting this 25 milliliters to moles. So I'm going to start with, okay, I'm going to start with 0.0415. I like to write out my molarity in its like units form so I can see what exactly is canceling out. So this molarity means that many moles per 1,000 milliliters, which is the same as 1 liter. I just put it in milliliters because I'm going to be using milliliters next for the 25 and I want it to cancel out easily. So if I have this molarity and that many milliliters of it, I can find the moles of hydroxide ions I have. Point, oh, I'm sorry, 0.00104. This is how many moles of hydroxide I have, and that means that that's how many moles of hydrogen ions I need in order to neutralize the solution. So, like, those values need to be equal. So next, I'm going to use my molarity of sulfuric acid to determine the volume of sulfuric acid I need to get 0.00104 moles, because I need my moles to be equal. So I'm going to do 0.00104 moles of hydrogen are needed. And what do I have? I have 0.144 moles of hydrogen in 1,000 milliliters of solution. So that allows me to solve for, like when I solve that, I get 7.2 milliliters. So that means that I need 7.2 milliliters of this sulfuric acid in order to react with my barium hydroxide to form water. So basically the steps here are solve for moles of hydroxide ions. That tells you that that's how many hydrogen ions you need. And then use the molarity of your acid, strong acid, to see how much volume of that strong acid you need to give us that number of hydrogen ions. And the thing to notice here is that both of these, see, the ratio of hydroxide ions to hydrogen ions in this is 1 to 1, since I have 2 hydrogen ions in my acid and 2 hydroxide ions in my base. So that tells you you can put those numbers equal to each other. Say you had barium hydroxide, but which has 2 hydroxides, but instead you had HCl, hydrochloric acid. Well, that only has 1 hydrogen per mole of acid. So that means you need 2 times the amount of moles of HCl than you do of barium hydroxide in order to neutralize both of those hydroxides. Let me know if that makes sense or if you want me to explain it again or in a different way, because I know that was a lot.